Hey guys, welcome to the Chapter 4 lecture video. So for this chapter, the study of chemical reactions, we're going to be skipping over quite a bit of material, as you can see here. The reason for that is it is sort of beyond the scope of what we're going to be learning. There's a lot of math we can do, right, looking at chemical reactions, a lot of reaction kinetics we can look at. But for the sake of time, for this class, we're going to basically skip over. So it's going to make chapter 4 pretty short overall. But it is a very important chapter because it is introducing us to chemical reactions in a way that we haven't really looked at molecules before. The primary one here we'll be looking at are radical reactions, and this pretty much only important for chapter 4. We might see it in other chapters as well, but it's going to primarily take place here. But it's still important to look at, and it's going to get us introduced to chemical reactions again in a way we haven't really thought of it before. So, right, thinking about chemical reactions, there's two different types we can consider. When looking at bond cleavage, we can think about heterolytic bond cleavage. So when a bond breaks and one atom gets all the electrons and the other atom does not. In this case, we use a double-headed arrow, like we have been doing, right, to show the transfer of two electrons. And so in this case, we get an anion and a cation, right? Now, the other type of bond cleavage, and we'll be talking primarily about that in this chapter, is homolytic bond cleavage. So the bond splits in half, and each atom gets one electron. And we emphasize this by using a single-headed arrow, right? Hopefully you can see the difference here. There's only one head of this arrow instead of two. And that is to denote there's only one electron moving, right? So in each of these cases, we have produced a radical. So we have an unpaired electron, right, which is very energetic. Because remember, from general chemistry, electrons like to be paired up when at all possible, right? Like with chlorine here, it has 3 lone pairs, but has 1 radical, right? And that's why we always see halogens bonded to just one thing, because that 1 electron they have right in their valence shell that's left over, that 7th electron, wants to make a shared pair, wants to make that covalent bond. So when we have radicals, we start getting into interesting chemical reactions, which we're going to be taking a look at in a bit more detail. So before we get there, we have to think about some of these reactive carbon intermediates, including radicals. We're also going to talk a little bit about the cation and anions formed when we have carbon intermediates. So the first one we're going to consider is carbocations. So these are carbons, as you imagine, with a positive charge. Okay, so when we're thinking about them, and just for note, I would be using R here as a term for an atom, and this means any number of carbons. Okay. So when we look at carbocations, we want to be able to tell which carbocation is more stable than the other. And so to do that, we have to draw out carbon with a different number of carbons and hydrogens attached to them. So hopefully this will become clear as I start drawing them out, right? So first we have a tertiary carbocation, right, with a carbon bonded to 3 other carbons. We have a secondary carbocation, a primary carbocation with just 1 carbon attached to it, and then a carbocation with no other carbons attached to it. And so we can actually rank these in terms of stability. We can say that this tertiary carbocation is more stable than a secondary, more stable than a primary, and the least stable carbocation is one without any carbons attached to them. Okay, so we're going from most stable to least stable. Now, why is that, right? It's good enough that we can just say, okay, when there's more carbons attached to a carbocation, that is more stable. There's a couple different ways we can think about it. The first way, and let's just do a simple carbon with 3 CH3s attached to it, 3 methyl groups. I'm actually going to draw out the hydrogens on this last one here. If you remember from general chemistry, remembering our periodic trends, we know that carbon is more electronegative than hydrogen. Not by a whole lot, and it's not always very relevant, but it is more electronegative. So, because of that, all these carbons have a slight partial negative charge, right? So something going on here called, we can call this hyperconjugation, which essentially means that there is some delocalization of that positive charge, quote unquote, because we have these partial negatives, right, kind of balancing out the positive charge from the central carbon. Right, so the less carbons we have attached to our central carbocation, the less stable it's going to be because there's less partial negative interactions happening with the positive charge. The other way to think about it is looking at molecular orbitals, which I know is everyone's favorite topic. So if we're looking at this carbon here, right, we're going to look at this carbon again. Right, we have to remember that this carbocation is only sp2 hybridized, right? It has an empty p orbital. Okay, and so when we're looking at the other carbon, right, we know that this is making sp3 bonds. Okay, there's a little back lobe there, and so we know that there is, right, from hyperconjugation, we know that there is some interaction happening here, right, kind of like what you see with a pi bond. It's not making a full pi bond, but there is some stabilizing interaction here with the same phase of the lobe from this sp3 orbital interacting with this unhybridized p orbital from that central carbocation. Okay, this doesn't happen with just hydrogen, right? So if instead, right, let's pretend that this is a hydrogen, we no longer have that stabilizing interaction because the only thing happening here with this hydrogen is that s orbital, right? And it's already in coordination with the sp2 orbital that's connecting, right, the carbocation to that hydrogen, right? So there's no other interactions that can take place. But here with the sp3 bond connecting the hydrogen to the carbon, there is that stabilizing hyperconjugation effect happening, okay? So simply put, the more carbons attached to a carbocation, the more stable the molecule is. And of course, we can also think about things like resonance as well. So we have a tertiary carbocation that can also interact with resonance. That's going to be more stable than a carbocation on its own, right? So kind of like thinking about acid-base reactions, right? Remembering with the conjugate base, if there was an opportunity for resonance, that was going to make a much more stable conjugate base. Okay, and we'll get into some examples of this later on. So we can get to practice in trying to figure out which carbocation is more stable than another. So inversely, right, let's look at carbanions, right? And so this is the exact opposite of the carbocation, right? So I'm going to not spend too much time talking about it. So for the different anions, right, carbanions, negatively charged carbons, the more carbons attached to the carbanion, the less stable it is, right? And it's for the exact same reason where those carbons coming off of the central carbanion, right, are partially negative. So in this case, I'll do this in blue, in this case, the less carbons attached to a carbanion, the more stable it is, right? So this is just inversed. And the same thing applies where if there is an opportunity for resonance, that will be more stable, right? Because we can delocalize that charge throughout the molecule. But in general, this is how things are going to be, where the less carbons attached to a carbanion, the more stable it is than a carbanion with more carbons attached to it. So now we're going to look at carbon radicals. And so carbon radicals actually are going to behave in the same way as a carbocation. where the more carbons attached, the more stable the carbon radical is. And that is because, for a very similar reason, right? In this case, carbon isn't charged. Right, remembering our rules for formal charge, our carbon with a lone electron, right? It has 4 electrons around it that it owns. We know that carbon has 4 valence electrons, so that comes out to 4 minus 4, which is 0. However, right, carbon still has, right, carbon radical, right, only has 7 electrons around it, right, and it needs 8. So that means that, again, like in the same case with the carbocation, the carbons surrounding the carbon radical are going to help stabilize the carbon radical, right? Because these carbons, right, again, they're designated for R for any number of carbons, could be 1, could be 20. They're partially negative, so it helps to sort of stabilize that central carbon, right? Giving it more slight negative charge, right? And so that's going to help it sort of feel its octet more fulfilled. Okay? And we can also think about resonance for carbon ions. And we'll get into that in a little bit. But yes, so just like with the carbocation, the more carbons attached to a carbon radical, the more stable it is. So really quickly, we can also think about, now that we know how radicals work a little better, we can also think about how to make them, okay? And so to do that, we have to consider different ways. One way is through light irradiation. So if we had Cl2, for example, and this will be a really common theme with halogens becoming radicals. How do we get from there to there, right? How do we go from chlorine with a happy covalent bond, 8 electrons around it, and its outer shell having a good octet, to a chlorine atom with a radical? And the way it happens is because halogens typically are much more readily able to undergo homolytic bond cleavage than other types of molecules. And so what we can say here, right, for light irradiation, we say H nu, okay? And that's just how it is. And that comes from the term for the energy of a photon. We will get into the math here, but that comes from the term H, which is Planck's constant, and this new term here, Nu, which just looks like a V. This is the frequency of a photon, okay? So when we have, the sort of HV symbol here, that just means light. And so what happens is light causes this bond between the 2 chlorines to break, and then we end up with our 2 chlorine radicals, okay? The other way to get a chlorine radical, or any radical, is through heat, or pyrolysis, which literally means heat, and then lysis means break. So again, with our chlorine, we would say, okay, heat. Right, so this delta term here means heat to get our 2 chlorine radicals. You notice I'm not putting in the lone pairs here, and that's fine. But when you have a radical, you always have to show it, okay? But you don't need to show the lone pairs. And so that happens through a couple different ways. With just heat, you don't always end up getting a radical to form. Typically, you have to use something else called a radical initiator. So anytime you see this delta term heat, it'll probably be an accompaniment with one of these. And we don't need to worry too much about the actual process for forming for how these radical initiators work. It is a little bit complicated, especially in the case with this one here, this azo compound, right, which just means nitrogen double bonded to nitrogen. But typically you will just see this over a reaction arrow. And this just means that the heat is helping with the radical initiator to make the radical reaction happen. Okay, and we'll talk more about this in the next video when we start actually looking into these radical reactions a bit more and looking at their mechanisms. But this is just so you guys know, especially if you're looking at the book, that when you have any one of these above the reaction area with heat, it just means that it is a radical initiator to help the radical reaction actually happen. Okay, so for some examples that we'll do together, take a look at these three problems and comparing the two, which one is more stable? Okay, so take a look back at the reactive carbon intermediate section of this and remembering the different rules. Again, remembering that just like with conjugate bases, we can look at one molecule versus another and say, okay, is this negative charge more delocalized? Is this positive charge more delocalized? Is this radical now more delocalized through a molecule? Okay, and we can come to the answer of which molecule is more stable.